So LeetCode 968 binary tree cameras. In this problem, you're given a binary tree and you can place some cameras on nodes, and a camera can monitor its parent, itself, and its children, its immediate children. Now what you need to do is calculate the minimum number of cameras to install in this binary tree so that all of the nodes are monitored. And here I'll present a simple solution that just goes through all of the possibilities of where you can place your cameras. So we're gonna go ahead and implement a recursive function that, when called on a node of your tree, returns this, the minimum number of cameras to cover that tree. And your state of your search of this minimum number is just the current node on which you are, and if the current node is already covered by a camera or not. So this is going to be 0 if the current node is not covered by a camera, and it's going to be 1 if it is already covered by a camera. Okay, so let's implement this recursive solution. Then we will implement the caching, which will make this a dynamic programming algorithm. So first thing, obviously, since this is a recursive solution, we're going to have our base cases. So the first case is when you don't have anything, you don't have a node, and so there's no cameras to be installed, so that's return 0. And then the second base case is where your current node is covered already by something and you don't have any children. So because of that, you can just return 0 because you're already covered. Okay, and now comes the actual recursion. So we're gonna have our best result, and then we're gonna do some attempts. We're gonna install our cameras somewhere, and we're going to update this best with the installation that makes the most sense. So we're gonna minimize the amount of cameras that are needed to install. Okay, so the first thing that we can do, and of course at the end we're gonna return the best, which we have minimized. Okay, so the first thing that we can do is we can install one camera on ourselves. And in that case, we have just installed one camera, and we can now have the same function call on our children, and they are already covered, and they are covered by us, by the camera installed on this node, right? So this is one of the things that we can do. So install a camera on our node, and then check how many cameras are needed for the left and right subtrees, and note that they are already covered by our camera. Okay, then one more thing that we can do is we can install a camera on our left child, and this can only be done if we have a left child. So we're gonna check if we have a left child. If so, then we can place a camera on it, and this will also cover us. And it doesn't matter if we are already covered or not. We can always do this operation. We can always install a camera on our left child if we have one, even if we are already covered. Okay, so in that case, since we've installed one on the left child, then the right child is no longer covered, obviously, and we don't have to call anything on the left child. We have to call on its children. So we installed one on root.left, and so now we need to check how many cameras it takes for its children. So root left.left and root left.right. And notice that again they are covered because we've just installed a camera on root left, so they are already covered, while root right is not. Okay, then we can do the same for the right child. So again, if we have a root right child, then we can install a camera on it. And in that case, it's going to be the same. The left children doesn't get covered. The left child doesn't get covered, but the children of the right child get covered. Okay, and we've installed one camera, so we add one to the total. And then the only remaining thing that we can do is, if we are already covered, then we don't need to place a camera that covers us. And so in that case, we can just call dynamic programming of root.left and the solution of root.right. So since we are already covered, it doesn't matter, we don't care if there is a camera here or here, because even if there isn't, we are already covered. So it's fine, right? So these are going to be calculated independently as if they were two completely separate trees. And their sum is going to be our result because we are already covered by some camera, maybe by our parent. Okay? And yeah, this is it already. So this is all of the things that you can do, and you're just minimizing a variable with the best one. So you just literally, there's no strategy at all. You're just trying, okay, what if I install a camera on me, on the root node? What if I install a camera on the left child? What if I do on the right child? And what if I don't care at all because I'm already covered? And so I just say, okay, do whatever you want, and I'll just take the best because I don't care. I'm already covered. So do whatever you want, right? These are just the possibilities. And now you just need to introduce caching or memoization, and that will give you the dynamic programming algorithm with a runtime complexity of O of n. Okay, so to implement the caching, you're gonna need a unique identifier for each node. So we're gonna do that by having a visit. So I'm gonna start with the ID of 1, and then I'm gonna call a recursive visit on all of my nodes. And it's just a very simple recursive function. If I have nothing, no node, I just return. Otherwise, I set my ID to be this variable plus, and then I increment that variable. So these are going to be 1, 2, 3, and so on. And then I just call myself on my children. And now we have unique identifiers on each node. And so we can build a cache array. And notice that since our state is two-dimensional, we have our ID of the current node that we are solving, and we have if it is covered or not. So we need two cached values for each unique identifier. Okay, so the cache is two-dimensional. And now what you can do is, instead of actually doing the computation, you can check if you already have the solution in your cache, and if so, then you can return it. Otherwise, do the computation, and don't forget to update your cache like this. Okay? And that's it. So I'll submit the solution to show you that it works. And again, the time complexity is O of n, because you're going through every node at most twice. One time for the case where it is not covered, and the other time for the case where it is covered. And the other times are just going to be covered by this cache check. So you're never going to do the computation again. So yeah, that's it. Thank you for watching, and bye.